the love of you. It won't be a stylish marriage, I can't afford a carriage, but you look sweet upon the seat of a bicycle built for two.
That was an IBM 7000 series computer singing the song Daisy Bell back in 1961. It's also said to be the inspiration to Stanley Kubrick to incorporate that song in his film 2001: A Space Odyssey some 6 years later. In the film, the spaceship's onboard HAL 9000 computer sings Daisy Bell on its deathbed. The IBM 7000 series started off in the early to mid 1950s as the models 704 and 709, which were first generation vacuum tube devices. Right at the end of the 50s, the second generation IBM 7090 was introduced. It used transistors on circuit boards like these. These are called SMS cards, a standard modular system. Then in 1962, the 7094 was introduced, which was an upgraded version, and finally culminating in the 7094 Model 2, which was the most powerful version in 1964. In 63 there was a couple of smaller ones made, the 7040 and 7044, and production of this series continued until about 1969. But in 1964 IBM introduced the System 360, which obsoleted all of this 7000 stuff. So for a time the IBM 7000 series was the most powerful and most widely used large-scale computer system in the world. There are about 250 7094s made of both models, and all up the 7000 series probably ran into the thousands. But today there's only about 3 left that I know of, which makes it hard for you and I to get our hands on one of them. But don't give up. You too can still have an IBM 7000 series computer living on your desktop. It won't be able to sing, but it will be able to compile and run programs written in Cobol, Fortran and Assembler. And here's how you do it with a IBM 7094 emulator program. This one's called B7094. Which I originally wrote back in the early 2000s, but it's resurfaced as a new project to make it presentable to a larger audience. So I'll just describe some of the forms we have here. First of all, we have the main console with all the blinking lights, which flash as programs run. And they're not just dummies, they're actually showing what's going on inside the thing. Then we have a virtual card reader, currently empty, a line printer, a bank of tape drives. Each one of these 7 things here is a tape drive. They're the emulated hardware or the virtual hardware. Then we have a couple of screens that belong to the emulator, which is the control panel that controls what we can see, and a tape viewer that lets us look at what's on these tapes. Obviously we can see what's on the printer and on the card reader, but to look at tapes we need this. So I'll run another job so we can see the cards. So here we can see a job that will print prime numbers. It uses the Fortran compiler to do it, and here in the card reader we have the job to do it. Cards are read from the bottom, so this is the first card, and up the top there is the last card in the deck. So these first ones, starting with dollar signs, are job control for the operating system, and the last of those is IBFTC, which means run the Fortran compiler. The Fortran compiler then starts reading the following cards, which are Fortran source statements, until it encounters that squiggle, that tilde, which is an end of file mark. it returns control to the operating system called IBSys, which then doesn't do anything. So now we'll tell it to run, and you'll see those cards being consumed by the compiler, and then when it runs we'll see output here on the printer. Here we go. Tapes have been mounted, cards got read, compiler's now running. At some point it'll say execution, there we go. Now it's running the program it compiled, and it's written the output not to the printer but to a tape, and there's the output on tape of all the prime numbers up to 10,000, I believe. Up to 10,000. It also contains all the output from the compiler. The reason it's on the tape rather than on the printer is because these IBM 7000 series computers were extremely expensive to buy and to run. So they didn't want them sitting around doing mundane stuff like reading cards and printing to a printer. They wanted to have it running flat chat using the CPU. So the I/O stuff, reading cards and printing, were typically done on an offline smaller computer, a 1401, as mentioned here. The 1401 read the cards, wrote them to tape. The tape was brought in to the 7000 series machine, and it read its input off the tape and produced its output on another tape. That tape was then taken back to the 1401 and it did the printing. However, this job read its input from cards. Let's try another one. Here's another prime number generator, so run him. This one, I believe, his output comes on the printer. Yep, there it is. Bit slow because it's doing line by line. But we've got the output from the compiler still is on the tape. And here's one that calculates pi. It's not very good. In fact, it's rotten. I'll show you in a sec why. Again, I believe the output goes to tape. Execution, so all that was compiling, now it's executing, and here's the results. It used the Leibniz formula to come up with that, which is, as you can see, is not very accurate. Then it used another algorithm, the Wallace product, again not very good. And the best way of coming up with pi turned out to be dividing 355 by 113, which is the best way. It's far better than 22 divided by 7, which is only good to, I think, 3 significant figures, whereas 355 divided by 113 is good to about 7. And here it is just printing pi. No calculation, was just given the value and it printed it. And here's just text of what pi really should be. And as you can see, this one, the simple divide 355 by 113, produced the best result. I don't know if that's a bug in the emulator, maybe the floating point system has a issue, or maybe it's simply not capable of accuracy beyond that. Another little feature is we can look at the core memory of the thing while it's running. So this one runs that second demo, but this time it shows the core. Now that black is unused. The blue is where it's written to memory locations. The green is where it's read from memory locations. And you can see little white dots flashing around all over the place. That's when it's reading instructions from that location. So it's jumping all over the place. Little subroutine there, I guess, whizzing through that, jumping here, running, jumping there, all over the place. This is still compiling. Of course, this display is a huge overhead, so it's running considerably slower than normal. But it will eventually finish compiling and then start running, which should be any second now. speed this up. Okay, now it's clearing core and started executing. So now the prime number program generated by the compiler is running. Now I'm guessing that maybe this area here is the prime number program created by the compiler, and this here is the operating system, and the compiler is calling upon the operating system to do printing. So that's why the little white execution location is flashing backwards and forwards between the two. Now if I turn off the core plot, suddenly it will run considerably faster. See the speed of the output there. Turn off core plot and it goes much faster until we get to the highest prime below 10,000, and there we go, done. Now as you can see, it's a fairly graphical emulator. It could perhaps be more so by having little round tape reels whizzing about, but there could be up to 10 tape drives. That would take a lot of room, and there's a lot of forms. We're not seeing all of them here, so there's plenty of windows. Remember, these things, the real machines filled whole rooms, so there's a lot to look at, and yeah, some compromises had to be made in how much we can display. Now, this is not the only emulator for 7000 series machines around. There are others, but I haven't used them, so I don't know. I know very, very little about them, but as I understand them, they are not graphical like this. They're command line based things, and I suspect, but once again, don't quote me, I'm not sure about this, but I suspect that they need a higher level of knowledge about these old systems and the emulators themselves in order to be able to do much with them, as opposed to this one. I've deliberately made this as simple as possible to use. That's why it's got this scripting bizzo. You really just, to operate this, you just download, extract, run the exe and just start clicking stuff. It's as simple as that. So there's really no excuse for not trying it out. This one's written in Pascal. The others are written in C, I believe. There's full sources included in the extracted folders. We won't go into compiling it in this video. I'll describe how you do that in the next one. But yeah, this thing runs on Windows only, but I believe it can be compiled for other platforms. And I'm told this exe runs in Linux under Wine. Also, it doesn't write to the registry. If you download it and don't like it, you can just delete the folder and it's completely gone. The other emulators around, the other programs are a bit more sophisticated. They implement discs and drums, which this doesn't, and part of doing that is implementing the 7909 data channel, which is not included in this one. This one uses I think 7607 data channel, which is considerably simpler apparently. So it would take a bit of work to make this thing emulate the 7909 data channel and discs and drums. But if it did, it would then be able to run CTSS, which is a time-sharing system, and the other emulators can run it. So perhaps once we've described how to compile this thing, someone very motivated may choose to tackle that challenge of making this thing run CTSS. Okay, I'll show a few more demos. That was all Fortran. Now we can do some Cobol, and the simplest thing, of course, is the Hello World program. And there we see the source again. Job control, IBCBC, which means execute the Cobol compiler, and there we have Cobol source. End of job. So we'll run him, and he prints his output on the printer.
chugging away compiling in the second execution, and then hello world, there's his output. And here's the output from the compiler written to tape. We have another prime number generator written in Cobol this time. This one puts his output to to printer, and instead of one number per line, it puts many on a line, so we have less output lines. And there we go, up to 10,000. The editor function. So I'm going to edit this script, the part of it that runs this prime number job, and here we go. Now this is a very unsophisticated editor. We've got to go up to files, scripts, here we are, Cobol EC7. Very unsophisticated editor, it's just a memo control, but it works quite nicely, and I've done a lot of editing with it, and it's been fairly easy to use. So just for fun, I'm going to change that 10,000 to 20,000. Those three lines there, text load 20,000 and text load end, are all part of getting that single card 20,000 into the deck that gets compiled. Now I think it has to be right justified like that inside a field of 6 characters. So we'll save that, and now because I've altered this script, we've got to return to the previous screen, which is a different file, and now when we go into that script again, we're back. We've reloaded the new version of the file with the updated value in it. So we'll run it and look at in the card deck that it's produced, and we should see 20,000 there. Right, so it's good. Let's run it. And there it is, showing the parameter card 20,000 and generating primes up to 20,000. Next thing to try is, let's edit not a script this time, but a source deck. So we'll go up to files, down to cards, and get that hello program, and change that to Goodbye Cruel World. Save it, and because that's a completely different file to this, we don't have to do any backtracking to reload it. We'll just run this and it'll pick up that file when it generates the deck, and it automatically closes the editor when it runs. And if we look at that deck, we should see that text has been altered. There we go, and compile and run, and there we go. Goodbye Cruel World. Now, nobody likes a suicidal computer, so let's take its mind off its problems and give it a different problem. We'll run this Cobol program to copy cards to tape. Now if we look at the deck generated, there's the usual stuff, the JCL to get the compiler happening, and there's the source to the compiler, and $CB end, and the squiggle, which is the end of file. When the compiled program starts running, it will read these cards as parameters and write them to a tape, and until it reaches end of file of the cards, indicated by that squiggle. So we'll run it, and it'll open up another tape unit there. No, underneath that one. We'll only see it for an instant before it gets covered by the tape viewer. And there it is. We're looking at the tape that was created there, Scratch B7, and there's the cards that were, the card images read from the reader, written to tape. Now we'll read that and print the card images on the printer. So there's a program for that. Run him, and there we go. There's the cards from the tape listed onto the printer. Now I mentioned the 2 other emulators that are able to run the CTSS system. They were written by Dave Pitts, one of them, and another by Richard Cornwell. And Richard has allowed me to use some of the jobs that came from his site, and let's have a look at those. One of them is a Fortran 4 program to generate magic squares, so we'll run that. And there's the output. Now, a magic square is where if you add the numbers along any row, any of the 4 rows, any of the 4 columns, either of the 2 diagonals, the 4 numbers in the center, or the 4 numbers at the corners, they all add up to the same value, which for that particular magic square is 34. And there's a bunch of others. And somehow they were generated from those parameter cards that the program accepted. No idea what the format of those cards is, but yeah, that's quite a nice little demo. Now we have a least squares curve fitting program. Now, when this starts, you see here it says, watch for a little mainframe computer folklore humour. So as an enticement, as an incentive for you to download this program and run it, I won't show you that. I'll let it run, but I'm going to edit out that bit, and I'll just show you the results at the end. And there we have the results. Now, yes, you didn't see the humour. You will when you download it and run it yourself. What's interesting about this one is it does a little bit of graphics, a couple of plots. Pretty rudimentary, but it shows that you can do some sort of graphics with this thing. And it was also quite a long running program. It's probably the longest, well it certainly is, I think, the longest running job in any of these demos. And if we just reload the source again, yeah, the source is on a tape. So let's have a look, yeah, there's the source. So it's Fortran, but it also calls subroutines which are written in assembler, and it uses FAP, no, not what you're thinking, to execute, to compile or assemble these subroutines. I'm trying to find one. Yeah, there's a bit of assembler. So this job includes multiple Fortran compilations and multiple assemblies, and somehow combines them all together and gives you a running object program. So yeah, that's a pretty sophisticated example. There's another one here, the Aggregate Production and Workforce Coefficients program, and if you know what that means, good on you. I have no idea. So we'll just run that. And there's the output from it. Nothing too amazing, and who knows what it means. Yes, it was Fortran 2. So if we look at the input tape that it used, execute Fortran, $execute Fortran. So that was invoked differently to the Fortran 4, which, if we look at the example of that, is invoked by IBFTC. Now there's one other here, another Fortran 2 program that uses FAP as well. There's an issue with that at the moment, so I won't try and run it, but by the time this video is published, that will be resolved. There'll be a link to where all this stuff is, where this whole thing is available. I haven't decided where to make it available from yet, but by the time I publish this, the link to it will be down in the doobly-doo below, along with links to the sites for the other emulators. There's a few system utilities. I don't know much about these, but it uses one of the standard operating system utilities, IBEdit, to do something with library tapes. to list the contents of syslib1 while at the same time making a copy of the tape. Okay, there you go. So this runs for quite a while too. There we go, and it's produced a listing of what's on that syslib1 tape. Right, so you can display these files in either BCD or binary. BCD is for character type stuff like source files, and binary is for programs like the operating system, etc. And this thing doesn't make much sense either way, because you have to understand what all this is. But there it is as hex, as octal, and as BCD characters. So there's all sorts of stuff in there. If we look at this one, which is, that is BCD, right? It's proper text. If we look at that as binary, we can see the text in the characters column. So they're just two different ways of viewing the contents of the tape. And you can save all this stuff to a PC disk file. Alright, there's another one. I won't go through these, I'll leave them for you to play with when you download this thing. There's also a couple of diagnostics. I don't know anything about these. I don't know if they're working properly. I think they generate some sort of an error. Now see that funny format up there? That was similar to what we just saw with tapes. That was called column binary format, which is a way of putting binary rather than text data on cards. And of course it looks like gibberish. That diagnostic 9M21 looks like it found some errors. Don't know anything about these, but Richard Cornwell's site has quite a bit of documentation on these diagnostics, so I'll leave that for interested parties to follow through on. This project was started back in the early 2001, 2004, and it was written in Delphi, which is a type of Pascal. The trouble with Delphi is it's hideously expensive, and because it's so expensive, some people produced a work-alike called Free Pascal and a interactive development environment called Lazarus, and it's very, very good. It's easy to forget you're not using Delphi when you're using those things, and it's all free. It's all open source and it's free, so it's a huge improvement on having to have Delphi to be able to compile this emulator. And we can do that thanks to Jim Falinger, who has been instrumental all along the way with this project. Back in the early days, he fixed bugs with the channel emulation and got the compilers to run for the first time, so that was great. And then more recently, he ported this thing to Lazarus and Free Pascal, thus making it possible for many others to be able to use it, and has also made numerous contributions to these demonstration jobs and scripts. So thanks, Jim, very much for all that, for all those efforts. Also back in the day, Mike Hoare wrote the floating point emulation part of this program, which is something I'm not sure I would have been able to do. It's fairly complex stuff, so thanks to Mike also. But right at the very beginning, how did this start? I stumbled across some documentation scanned by, I believe it was Al Kossow, who I also believe is associated with bitsavers.org, or maybe he founded that. I'm not sure of the details. It's all a bit hazy now, but a lot of information was scanned, both for the 7000 series stuff, but numerous other old pieces of computer hardware. But chief amongst this was the principles of operation for the 7000 series. Now, that document, that manual, makes it possible to write an emulator for this system. And that caught my eye, and I thought, oh, wow, this would be great. I could write an emulator. But then what would be the point if you don't have any software to run on it? And then I stumbled across Paul Pierce's site, who actually owned a real 7094 system and a lot of other stuff. He's since donated it to a museum. But Paul also had the great foresight to record the tapes that came with those real systems, these 7-track 2400-foot tapes. He actually made a contraption to read them and save that data and made it all available on his website. And also, I think he made another contraption to read the card decks and made those available as well. So huge thanks to Paul for doing all that. And so the availability of the documentation for these systems and some software to run on it made it possible or viable to go ahead and write an emulator for it, which is what I did. Paul also wrote an emulator as well, but I don't think he went very far with it. Now, this 7000 series stuff was once the most common large-scale computer system in the world around the early 1960s, and consequently the operating system, IBSys, was the most widely used operating system, like Windows or maybe it's Android today. I'm not sure when the last 7000 series was turned off, but probably in the mid to late 1970s, possibly the early 1980s, not very sure on that. So IBSys, which was once the most common operating system in the world, gradually ceased operation and then never ran anywhere for 2, maybe even 3 decades, until at 15:27 Australian Eastern Standard Time on the 14th day of May in the year of our Lord 2004, the IBSys operating system at last ran again for the first time in over 20 years, possibly even 25 to 30 years, under this emulator on my little PC. I was pretty pleased with myself for doing that. Now, it didn't do much, just complained that it needed some control cards in its reader. I mean, it had been asleep for a long time and it now wanted its breakfast. But at least it had run, and with the help of Jim and others, it now does a lot more. So perhaps I should show you how to install this thing once you download it. You are going to download it, aren't you? Yes. So I'll turn all this off and start from the top. So to install B7094, from the link down in the doobly-doo, you get a RAR file and you simply stick it somewhere and extract it. Which creates a folder which has a structure, which I'll describe in a second. I'm doing all this on a flash drive, that's why it's a bit slow. Right, there it is, and if we look at the folder structure, it has output, that's where everything that this emulator generates goes, so initially that'll be empty. IBM manuals, which is also empty, I believe. I might put something in there, but so probably the best thing to do is to go to bitsavers.org and look at all the manuals there, or go to Richard Cornwell's site where there's a lot of documentation as well. Files is the important bit. We'll get to that. Docs, there might be a bit of scribble there. All this stuff is well out of date, but we might. I might update that. I'm not sure. Build is the source stuff. We won't go into that for now, but that's where you'll go to compile this thing. It's included in the download, but wait for the next video on how to use it. And the actual emulator is here. That ini file is just won't that initially that ini file won't be there. It's created when it first runs. But, the files is the most important. It contains 3 subfolders: tapes, which contains the system tapes and diagnostic tapes. Most of it, what it uses will be these 2 here, ASYS8 and ASYS1. They're the IBSYS system and library tapes, I believe. Cards contains all the JCL, well, there aren't many jobs actually. The scripts, which we'll get to, they create the jobs. So most of these are just pure card decks, source files. And in the scripts, these are the emulator script programs that you've seen running all along, and they wrap those card decks with JCL and stick it to the appropriate place. So that's all you do. You download the RAR, extract it, go to the bin folder and run the exe. And there it is. Introduction and Fortran, Cobol, Richard Cornwell stuff. Now this console here is actually modelled more on a IBM 7040, 7044 system than the 7094, which is a desk style console. This was stuck on the end of the main computer box. You didn't sit down in front of it like you do with the 7094. And the reason I did this is because this is the one I knew. At Melbourne University they had a 7040 or 7044, which I saw as a kid, and that got me very fascinated with computers, and it's sort of stuck ever since. And some years later I ended up acquiring the actual gizzards of that computer, which I pulled apart for the gold. And I've only just recently, another 35 years beyond that, finally finished processing that stuff. It was a lot of it was sitting in my backyard for 30 years doing nothing, but I finally processed it. So yeah, there you have it, the IBM B7094 emulator. I hope you enjoyed that. I do hope you download it and have a play of it. It's very simple to do, and you don't need to know anything about this stuff to enjoy it. So there's no excuse for not doing it. So yeah, I hope you enjoyed this video. If you did, please like it and subscribe, and I'll catch you later.